Continue on physical chemistry, chapter 18. We're in section 14 now. We're going to talk about a two-particle rigid rotor. Now, this isn't a realistic model, but again, it's a model we're going to use. So we have two masses a certain distance apart, distance r for radius, of course, and they're a certain distance. So we're going to ignore any possibility of vibrations. So that's why we call it rigid, because it can't vibrate. We're going to say that V is equal to 0. There's no potential energy. Now, r is the radius, but in the book it's d for distance. So we have the differential of V, is equal to minus FdR, is equal to 0, since the radius doesn't change. Okay, so that's why there's no potential energy. There's no change of potential energy. So we're going to say the energy is just the kinetic energy plus the rotational energy, since there's no potential energy. Now, the energy of the rotation is going to be equal to J times J plus 1 times h bar squared over 2I. That's capital I. So capital I is the moment of inertia. Mu is the reduced mass. And then J is going to be the rotational quantum number. And it can be 0, 1, 2, 3, etc. So it may seem strange, but we're going to be doing mu in grams. So when you have the two masses, the reduced mass is mass 1 times mass 2 divided by mass 1 plus mass 2. So the energy levels here, so we have energy. So for J equals 0, that's 0. There's just no energy. So there's no 0 point energy like we had in some other quantum systems. Then J equals 1, we get 2. J equals 2, we get 6. J equals 3, we get 12. So you notice these are tiny energy levels, but they get farther and farther apart. They're not evenly spaced. So energy, notice we're writing energy divided by h bar squared over 2I, so the units cancel out. So that's where these numbers come from. That's why there's no units. Now let's talk about polar coordinates. So let's say we had x, y, and z. So, and then we have a mass here, mass 1, and then another mass out here. Well, you could give let's say mass 1 is just the origin, 0, 0, 0, and x, y, z. The mass 2, you could give it x, y, z position of mass 2. But it's actually going to be easier to do some of the math in polar coordinates. So first, the straight line distance from M1 to M2, we already said we're going to use r for radius. Some, like I said, use d for distance. Then we're going to have the projection onto the xy plane, and you can see that's phi. And then you're also going to have the distance away from the z axis, and that's the theta angle. So we're going to convert, you can say x is equal to r sine theta cosine phi, and y is equal to r sine theta sine phi, and then z is just r cosine theta. Now the length of projection of r onto the xy plane, that's r sine theta. So that's where this part came on up here. Now Cipher rotation is the product of two other functions. So we have Cipher rotation, we have this of theta and this of theta. I forget what that symbol's called. But anyway, the formula for psi rotation doesn't include r, since r doesn't change. So r is a constant, remember, because we're talking about a rigid oscillator here, or a rigid bar. So this symbol, it depends on J and MJ, and this symbol just depends on MJ. Now MJ is the component of J along the Z axis. And remember, like I said already, I think J could be 0, 1, 2, 3, etc. Now MJ can be anything from minus J to J, but only integers too. So minus J plus 1, minus J plus 2, etc. So all the way to 0, then 1, 2, 3, J minus 1, all the way to J. So like for J is equal to 2, MJ can be minus 2, minus 1, 0, 1, or 2. That's 5 possibilities. So for a given J, there are 2J plus 1 values for MJ. So for example, for J equals to 1, MJ is equal to, it can be minus 1, or it can be 0, or it can be 1. So here we have J We have 0. We could say psi rotation 1, 0. Or we can have -1 for mj. Then we have psi rotation psi 1 minus 1. And then psi for mj plus 1, then we have psi rotation psi 1, 1. So for each, so this is all the same energy level. But so we say for each energy level j, it'll have 2j plus 1 degeneracy. Now let's say we're going to talk about hydrogen chloride, and we're going to pretend it's rigid, which is probably wrong, but we'll pretend. So if we have j is equal to 0, we have energy rotation is equal to 0. For j equals 1, we get energy of rotation is 4.17 times 10 to the negative 22 joules. So that change in energy between those two energy levels for rotation is obviously 4.17 times 10 to the negative 22 joules. And that's equivalent to microwave radiation. Now for comparison, let's say we have carbon sulfide, however you say that, or carbon sulfur bond. This isn't necessarily a whole atom, I guess. So again, for j is equal to 0, the energy rotation will be 0. For j is equal to 1, the energy of rotation will be 3.246 times 10 to the negative 23 joules. So obviously the change in energy between those two levels is 3.246 times 10 to the negative 23 joules. So now from that, we want to know what is the distance between the two. In other words, what is the bond length? Well, the energy for that is, remember, j times j plus 1 over h bar squared over 2I. And I is the reduced mass times r squared. So we get the change in energy. It's going to be equal to E1 minus E0. It's equal to 1 times 1 plus 1 times h bar squared over 2I minus 0 is equal to h bar squared over 2I. And then I is equal to h bar squared over the change in energy is equal to h squared over 2 pi squared times the change in energy. Then we put in the actual values. We get 6.63 times 10 to the negative 34 joules seconds squared divided by 2 pi squared times 3.246 times 10 to the negative 23 joules. So for I, we get 3.43 times 10 to the negative 46 joule second squared. So the reduced mass, remember, m1 times m2 divided by m1 plus m2. So we get 12 grams per mole divided by Avogadro's number to get the mass of one atom. And then same thing, we get 32 grams per mole divided by Avogadro's number to get, the grams per mole. So then we get 12 grams per mole divided by Avogadro's number plus 32 grams per mole. And that works out to 8.73 grams per mole divided by Avogadro's number, 6.02 times 10 to the positive 27 per mole. Obviously the per mole cancel out, which isn't a real unit, but you get the idea. So the reduced mass of that carbon-sulfur bond is 1.45 times 10 to the negative 23 grams. So remember, r squared is equal to I over mu. So now we can substitute in the numbers. We get 3.43 times 10 to the negative 46 joules second squared divided by 1.45 times 10 to the negative 26 kilograms. See, we have to get the units to match up right. So we get 2.37 times 10 to the negative 20 meters squared. Take the square root of that for r, obviously the positive square root, and we get 1.54 times 10 to the negative 10 meters, or 1.54 angstroms. And that's all for that section.